let's talk a little bit about how the address translation is actually done. So even though the pages are the same size in the virtual and the physical address spaces, the address spaces themselves might be different sizes. And so we need to be aware of that. We may need a different number of bits for the virtual address versus the physical address. So in order to facilitate this translation, we divide these addresses into different pieces. So within the page, we're going to have the page offset, so that's going to be the lower order bits of the address. And then we're going to use the higher order bits as the page numbers. And these are the actual things that we'll look up inside of the virtual page table. And so that is what's going to give us a physical page number, and then we can reassemble the full physical address by copying over the page offset, which is the offset within the page, and then the new physical page number, which we got from looking up the virtual page number. So this translation is accomplished by something called a memory management unit, or an MMU, and this is typically on chip on the CPU that is there so that the translation can happen as quickly as possible. It's typically assisted in this task by something called a translation look-aside buffer, which is really nothing more than just a small cache of page table entries. So all of the things that you learned about how caches work apply directly here, and it works in the exact same way as the caches we've talked already. And this, again, provides faster address translations because you don't have to go to the full page table, which is quite large, most of the time, if your program is exhibiting good locality. And, you know, at this point, you should sort of realize that it's sort of caches all the way down. This is really a core concept in computer architecture. A well-placed and well-designed cache can really speed up the performance of your system. Okay, so in the lab, we'll ask you to do some address translations with sort of a small sample system with an L1 cache. And so there are several different components that are involved in this translation. So we have the CPU that contains the ALU, the L1 cache, and the MMU and the TLB. So the MMU and the TLB handle the address translation, possibly with a lookup to the page table, which is generally in RAM. And then the data itself is either going to be in the L1 cache, it's going to be somewhere in DRAM, or it's going to be somewhere on the hard disk. And we're going to be focusing on the just the L1 cache and the DRAM in the lab. So here's what a lookup looks like. So the fast track is that we look up the address that we're trying to get to in the TLB, and it's there. So we can go ahead and get the physical page number directly from that cache, and then we can look up those addresses in the L1 cache to see if it's there as well. And if it is, then that's our fast track, and we can just grab the byte and we're done. If the data wasn't in the L1 cache, then we'll have to go out to main memory to load that line into the cache, and then we can access it from the cache. If the address that we're looking for is not in the TLB, we're going to have to go to the full page table and look up the physical page number there. Once we have that, then we can do the lookup as we did before. If there is no page number associated, that's when we have a page fault, and that means that we're actually going to have to go out to main memory or perhaps disk in order to load in the data and get it into both our cache and our TLB. So this is the entire process, and it's a little bit complicated, right? There's a lot of components going on, and so this is pretty cool that you've gotten this far in your study of computer systems, that you can sit down and work through what happens at this very low level with all of these really sophisticated components that have to talk to each other. But when it all works well, you have a really, really performant and capable system.